Okay, so still looking at our practice test here, and let's see, the sun is starting to change position here where I'm working on it. Make sure we can kind of see what's going on here. I think we can maybe finish up these last three questions on the 1-1 video here. So we'll see if we can manage to do that. Number 8 here, we were asked to identify oxidation numbers of each atom in the equation and then identify which atoms were oxidized or reduced. So this is potentially an oxidation reduction reaction, and we're looking to identify which species was oxidized, which was reduced. There's a set of rules here that you need to follow, right, related to ionic compounds, charges, right, and then there are rules for nonmetals when they're involved in different compounds. So let me try to spin just a little bit here to minimize the light from my window that is casting a shadow here on my page. So we have, I don't know if this is working. Let's try it this way. Maybe in the shade is better if it's all in the shade. I think that's pretty good. We can still see it. Iron hydroxide here, FeOH2. There's two hydroxides with this iron, so that would make the oxidation number of that iron +2, right? Just the charge in the ionic compound. Hydroxide ion, OH, has an overall -1 charge, and that fits with the rules for oxygen and hydrogen, that oxygen should be -2, hydrogen should be +1 in covalently connected compounds. The same applies for water. If you apply the rule for oxygen and the rule for hydrogen to water, oxygen is -2, hydrogen is +1. You add those together and water is a neutral molecule. The one that's a little different here is O2 here for oxygen, because that's the elemental form of oxygen. Elemental forms always have the oxidation number of 0. Now, if we move over to the product side, this is FeOH3, so this now is iron 3 hydroxide, and that means the iron here has a charge of +3, right? But hydroxide ion, that's still the same. That's oxygen -2, hydrogen +1, right? One oxygen, one hydrogen add together to give you a -1 ion in hydroxide. Now, with those oxidation numbers, the changes are in the iron atoms. So iron started at +2, ended up at +3. If you're getting more positive, that means you're losing electrons. So losing electrons is oxidation. The iron, we would say, was oxidized over the course of this reaction. The other change is to some of the oxygens. The oxygens here that started as elemental, they ended up as part of the hydroxide at the end. So they went from 0 to -2, and if you become negative, you're gaining electrons, and gaining electrons is reduction. So some of those oxygens, the ones that started in the elemental form, were reduced over the course of that reaction. So you need to know how to do all those things. There'll be one of those certainly on the test. Number 9 here. We want to predict the products of the following reaction, then write out the total and net ionic equations. So this essentially is what we talked about with precipitation reactions generally, although we mentioned different acid reactions as well. And we'll see one of those in the last question. But to get the total ionic equation, we want to start to separate all the pieces here. So ammonium carbonate, that's going to break apart into 2 ammonium ions, and each ammonium ion has a plus charge. Those would be aqueous. Carbonate, though, that's a polyatomic ion, so that'll stay together in solution, but we do want to indicate its -2 charge there when we've broken it up. Copper nitrate, looking at that formula, we can see that that's copper 2. So a +2 charge on that copper ion when it's in solution. And nitrate is a polyatomic ion, so the nitrates will stay together, but there'll be 2 nitrates floating in our solution. So there's the completed reactant side of our total ionic equation. Right? And that's a good place to start to think about what might happen in the reaction. our first cation here is ammonium, right? And it was soluble with carbonate. It's not going to interact with copper since they're both cations, but it could interact with nitrate. So we'd want to evaluate ammonium nitrate. Is that a soluble salt or an insoluble salt? And since ammonium salts and also nitrate salts are always soluble, those will remain soluble. So those are in fact going to be our spectator ions here in this reaction. So they'll be exactly the same on the product side. 2 ammonium cations are still floating around in aqueous solution, and 2 nitrate anions still floating around in aqueous solution. The copper, the other cation here, right, it was soluble with nitrate, but now it has a chance to interact with carbonate, and that in fact is going to be our solid. The rule for carbonates is they're usually insoluble, right? The exceptions are the first row metals, lithium, sodium, potassium, and ammonium as well. So copper carbonate is our solid. Now since the copper is +2 and carbonate is a -2 anion, we just need one of each to make the right formula, so just be CuCO3. Right? Now that would allow us to complete the molecular equation. Didn't really tell us to do that, but let's just do it anyway. Copper carbonate is one of our products. It's a solid. We already wrote that in a molecular form. Ammonium nitrate would be NH4 NO3. Don't need any parentheses since there's just one of each of those polyatomic ions. But to keep the equation balanced, we would need a 2 for a coefficient in front of them. Okay. Now we mentioned the spectator ions, ammonium and nitrate. They have the same phase on the reactant side and the product side. They're the spectator ions. That means we leave them out of the net ionic equation. So let me just underline them here. Right, if we leave those out, the other components, both of them were aqueous on the reactant side, but part of the solid on the product side. So that is the net ionic equation, kind of that concise version of the change that actually occurred in this reaction. Copper carbonate solid. Okay, now I'll want to see you guys do the same thing given a similar set of information. So I'll just give you the 2 reacting species, and I'll want you to be able to complete all these equations, get all the charges right, get all the phases right, predict the right products, which one's a solid, which one maybe isn't a solid, right? Identify the spectators, get to the net ionic equation at the end. We also want to do something similar with the acid reactions we talked about. So you should be ready for an acid reacting with a metal, an acid reacting with a carbonate, or an acid reacting with a base. And what we have here is an acid reacting with a base. So H3PO4, we see the hydrogen at the beginning of the formula, tells us that's an acid. In fact, that's phosphoric acid. Hydroxide ion is what indicates a base. So this is an acid-base reaction. We should know acid-base reactions, the products are water and a salt. So water is going to be one product, and water is always a liquid. At least at normal temperatures, right? This type of reaction, it's always a liquid. The salt is going to be a combination of the cation that comes from the base, which would be lithium, and the anion that comes from the acid, which would be phosphate. Now we should know phosphate has a -3 overall charge, so it will require 3 lithiums to make the product. The correct formula for that product will be Li3PO4. That's a lithium salt, so that should be aqueous in that particular reaction. But that's going to be important for balancing the equation. If we have 3 lithiums on this side, we need a 3 back here on this side, right? And that means 3 hydroxides and the 3 hydrogens from the acid, we'd get 3 waters. Now it is okay with 1 phosphoric acid and 1 lithium phosphate on the product side. So you do want to be able to do that. Predict the products and then make sure you balance the equation. Another thing you might think about here, we don't usually think about the total ionic equation for the acid reactions, but sometimes we do think about the net ionic equation. So really, lithium is soluble throughout this reaction, and phosphate is soluble throughout this reaction. The net ionic equation for an acid-base reaction is the hydroxide ion reacting with the H plus to form water. Right? And so even if there's 3 hydroxides and 3 H pluses, this is balanced without those prefixes. If it's just OH, H plus to water, that's the net ionic equation for any acid-base neutralization reaction. At least the ones we've talked about so far. Things will get more complicated when we start to think more deeply about what acid maybe is describing in terms of chemistry. Okay, that's the end of the practice problems for chapter 2. Probably worth reminding you, look at your study guide for all the topics that are fair game for the test. You can use that study guide as a good way to find more practice problems in the textbook or in one of the available online textbooks. And you'll have a review set of problems from lab as we approach the test as well to make sure you're ready for that particular test.